Good morning student, myself Mary Sakla, and in today's session we solve the example of column and strut. Okay, now we start with our example. Now first of all, start the example, we read the given data properly and which unknown values here we find out that we find. Okay, now first of all, column of circular section has an external diameter 200 mm. Okay, and the thickness is given 20 mm. Length of column is 4 meter and both end of column is hinge end. Column carries a load of 100 kilonewton and eccentricity of 20 mm. Okay, find the maximum stress on column section and also find eccentricity to avoid tension anywhere in the section, and Young's modulus E is given 110⁻³ Newton per mm square using appropriate formula. Okay guys, in this example, this is the example of column and strut, but in this example we find out maximum stress and also find out eccentricity to avoid tension anywhere in the section. So here we use another equation. First of all, we mention the given data here. D is equal to 200 mm. Okay, write down external diameter is given and that is 200 mm. Then thickness T is given 20 mm. Okay, and load P is given 100 kilonewton. So convert into Newton. 10⁻³ 100 into 10⁻³ Newton. Okay, and value of Young's modulus E is given 100 into 10⁻³ Newton per mm square. Okay, eccentricity E for here, eccentricity E is unknown, that we find out. Okay, and second values are given. Okay, write down here, both end of column are hinge. First of all, we find out effective length here. Write down both ends of column are hinge. Okay, so that LE is equal to L. Okay, and our L is given here 4 meters. Okay, so first of all, convert into mm. 1 meter is equal to 1000 mm, so 4 meter is equal to 4000 mm. Okay, right here LE is equal to L, that is equal to 4000 mm. Okay, now next, one by one we find out area, inertia, but here internal diameter is not given. So first of all, we find out internal diameter. What is the equation of capital D? Capital D is equal to D plus 2 times thickness. Now here we find out D, so capital D minus 2T. Okay, that is equal to 200 minus 2 into thickness 20. Okay, and is equal to 160 mm. Clear? Now we find out one by one another values. First we find out area, so write down here, area is equal to pi by 4 capital D square minus small d square. Put the values capital D and small d. Pi by 4, then 200 square minus 160 square, and my answer of this area is equal to 11,309.73 mm square. Okay, now we find out inertia. Write down inertia is equal to inertia for hollow circular section, pi by 64, then d raised to 4 minus d raised to 4 is equal to pi by 64 200 raised to 4 minus 160 raised to 4, and my answer of this inertia is equal to 46.37 into 10 raised to 6 mm raised to 4. Okay, now here we find out Z. Z is equal to our section modulus, and that is equal to I by Y. Now what is the value of Y here? Y is equal to maximum distance from center, that is capital D by 2, and capital D, that means our 200 by 2 is equal to 100 mm. Okay, next we find out our section modulus. So right here Z means section modulus. Okay, for we write down the full form of section modulus right here. Section modulus Z is equal to I by Y. I is equal to 46.37 10⁶ divided by 100 here, that is equal to 46.37 into 10⁴ mm cube, because inertia is equal to mm⁴ and y is equal to mm, ultimate mm cube. Okay, now next we find out our direct stress. Our first value is equal to direct stress, because in this example we find out maximum stress, and maximum stress is the summation of direct stress and bending stress. Okay, direct stress. Now direct stress is equal to sigma 0 is equal to load divided by area. Here load is given 100 into 10⁵, and area is equal to area of this given hollow rectangle circular section 11,309.73, and my answer of this direct stress is equal to 8.84 Newton per mm square. Okay, now second we find out bending stress right here. Bending stress sigma B is equal to m by z. Section modulus we already find out. Now equation of moment. Here our equation of moment is changed, that is PE, then sec LE by 2 under root of P by EI, because here eccentricity is given, and also this is the example of column and strut. So we can't take PE only, here we use this equation. Now one by one, first of all we simplify LE by 2 this term, LE by 2 under root of P by EI. Okay, now what is LE? LE is equal to 4000, so right here 4000 by 2 and under root, that means P is equal to 100 into 10⁵ divide by again E is equal to 100 into 10⁵, and I we find out value of I is equal to 46.37 into 10⁶. Clear? Now after simplification this answer is 0.2937. Okay, and this answer will be in radian. Okay, write down radian. Now we convert into degree, because here we find out ultimate the value of sec. Okay, 0.32937. 1 radian is equal to 180 degree by pi. Okay, if we convert degree into radian, then pi by 180, and if we convert radian into degree, then 180 degree by pi. Okay, now after simplification answer is equal to 16.2828 degree. Okay, now next we find out value of this sec. Okay, ultimate, this term is for our angle sec. Right here sec 16.828 degree. We in calci we can't take directly value of sec, so we convert sec into cos. So 1 by cos 16.828 degree is equal to, answer is equal to 1.044. Now my M is equal to PE sec LE by 2 under root P by EI. Now one by one put the values. P is equal to 100 into 10 raised to 3 and value of E is in given data, that is 20. Okay, and here we find out sec, that is 1.044. okay, and now my answer of this bending moment M. Okay, now what is the answer of this M? M is equal to, write down here, moment M is equal to 2089400, and what is the unit of this moment? That is equal to Newton mm. Okay, now next we find out bending stress. So right here, next bending stress. Okay, bending stress sigma B is equal to M by Z. M by Z, that means our section modulus. M is equal to 20,89,400 divided by section modulus, that is 46.37 into 10 raised to 4, and my answer of this sigma B is equal to 4.506. Clear? Now we find out second value, that is our sigma maximum. So right here, sigma max is equal to summation of direct stress plus bending stress. Now direct stress we find out 8.84 and bending stress we recently find out 4.506. okay, and summation of these two values is equal to sigma max is equal to 13.31 Newton per mm square. Okay, here we find out our first answer, that is sigma maximum. Now in data ask find out eccentricity that avoid tension anywhere in the section. Okay, so here we write down first our statement eccentricity. First of all, write down the heading eccentricity to avoid tension anywhere in the column section. Okay, and so that if you remember in theory portion, to avoid tension, our sigma minimum, our value of this sigma minimum is greater or equal to 0. But to solve the example, here we take sigma minimum is equal to 0. Now what is the equation of sigma minimum? That is equal to difference between direct stress and bending stress is equal to 0. Now simply direct stress is equal to our bending stress. Okay, now one by one, what is the equation of direct stress? Is equal to P by A, and here is the equation M by Z. Now we one by one we put the equation P by A. M is equal to PE sec LE by 2, then under root of P by EI and divide by Z. Clear? Now we have values, simply we put here unknown value is our eccentricity E. Now one by one, P is equal to 100 into 10 raised to 3, area is equal to 11,309.73 and load is given 100 into 10 raised to 3 and this E value is unknown into sec LE by 2 under root P by EI. We find out this value, that is 1.00. okay, final value is 1.044 and divide by our section modulus. Section modulus is equal to value of 46.37 10 raised to 4. Here we find out this unknown value E, and E is equal to 39.25 mm. Okay, this is our new eccentricity, and this eccentricity avoid tension anywhere in the section. Okay, our example is complete. This is our new type of example. Okay, now our last example of column and strut. Again, before solving this example, we read the given data properly and then we solve it. Column of size 400 by 800 mm. Okay, here our column section is given. Okay, and size of this column section is 400 mm by 300 mm. Okay, now one by one we write down here data. B is given 400 mm. Okay, and D is given 300 mm, and L is given 6 meters. So right here L is equal to 6 meter and 1 meter is equal to 1000 mm. So 6 meter is equal to 6000 mm. Okay, now both end of column is fixed. Okay, then determine the crippling load, and Young's modulus E is equal to 2 into 10 raised to 5. Okay, here alpha is not given, Rankine constant is not given, Fc is not given. That means this crippling load we find out by Euler's formula. If alpha and second Fc is given, then we follow Rankine formula. Okay, now both end of column, both ends fix. If our both ends fix, then LE is equal to L by 2. Now what is L? 6000 by 2. Okay, so LE is equal to 3000 mm. Okay, now what is the equation of Euler's formula? Pi square EI by LE square, and value of E is also given, that is 2 into 10 raised to 5 Newton per mm square. Okay, now one by one, here we find out two inertia because moment of section is rectangle. Okay, and from two values we consider lower one. Okay, first of all we find out inertia about x-axis, that is BD cube by 12, and second IYY is equal to DB cube by 12. Okay, now B is equal to 400 into 300 cube by 12, and my answer of this I axis 900 into 10 raised to 6, and unit is equal to mm raised to 4. Now second here 300 into 400 cube by 12, and answer is equal to 1.6 10 raised to 9 mm raised to 4. Okay, now from these two values, I axis is a minimum, I axis is our minimum inertia, that is equal to 900 into 10 raised to 6 mm raised to 4. Okay, now we find out our Euler's load. So write down here value of our Euler's equation, Euler's formula, right here heading Euler's formula is equal to PE is equal to pi square EI by LE square. Now one by one, pi square into E is equal to 2 into 10 raised to 5, and value of I we find out 900 into 10 raised to 6, and LE we find out 3000 square. And after solving, my Euler's load is equal to 118.93 10 raised to 6 Newton. If I want to convert this value in kilonewton, then Euler's load is equal to 118.93 10 raised to cube kilonewton. Okay, this is my Euler load. That Euler load, or what we can say crippling load. Okay, this is our Euler load. Okay, here our example is complete. Okay, in next session we start with our new chapter. All type of example we cover. Okay, just now we stop here.